Here we have a disc pulley that has a radius r and mass m. The surface between mass m2 and the ramp is not frictionless with coefficient of kinetic friction. The mass m2 slides down to the left while mass m1 moves upward. For letter A, derive an expression for the acceleration of the masses. For letter B, find the tensions T1 and T2. First we draw the FBD for each mass. Here we have for mass 1 and we note there are no forces along the x-axis, so it is just two forces, tension and weight 1. The second mass lies on a plane with friction and the block moves downward with acceleration A. Here the tension is labeled as T2 to differentiate from T1 earlier. Here we have considered that the tensions are different, or T1 is not the same as T2. Here we add an FBD for the pulley that relates the two masses through their tensions. So the pulley is a disc and it is allowed to rotate with an angular acceleration. Here we will assume the pulley as a disc with a moment of inertia. The next step is the summation of forces. We sum forces along the y-axis and we get that the tension 1 is equal to mass 1 times gravitational acceleration plus mass 1 times acceleration A. Next we sum the forces for mass 2. For the x-axis we have a negative tension, a negative friction and a positive weight component along x equals to mass times acceleration. We write an expression for tension 2 which is equal to the weight times sine theta minus the coefficient of friction times the normal force minus mass 2 times acceleration. To get an expression for the normal force we use the sum of forces along the y-axis, which we then substitute to the previous equation. So, the expression for the tension is simplified further as shown in equation B. For the pulley system, we use the sum of torque or net torque, which is equal to the moment of inertia times angular acceleration. So we have two forces and we examine which one causes the rotation clockwise and counterclockwise. So for tension 1 it can cause the disc to rotate counterclockwise, so it has a positive sign. For tension 2 it can cause the pulley to rotate clockwise, so it has a negative sign to indicate its direction of motion. Here the disc is assumed to have the same moment of inertia at its center of mass as a solid cylinder, which is equal to 1/2 times the mass times the radius. We also recall the expression of angular acceleration in relation to translational acceleration, or to be more specific, the tangential acceleration, as equal to the fraction of acceleration over the radius r. Substituting these equations we obtain equation D. We then use this expression and substitute the other two expressions of tension. Substituting the equations for the tension or equation A and B to equation D to get an expression for the acceleration. So, here we have a couple of steps to simplify equation D, so double check as you transpose terms, especially the signs. Written in at the bottom is the expression for the acceleration A. To determine the tension 1, we substitute the expression of acceleration obtained in the previous slides, or equation E, to equation A. So we simplify this expression of tension 1 as shown here. Similarly, to determine the tension 2 we also substitute the expression of acceleration obtained in the previous slides, or equation E, to equation B. So we simplify this expression of tension 2 as shown here. Both equations for the tensions are quite long, so it is important to double check your expressions and make sure that the terms contain all that is given in the problem.